I'd just like to say hi to everybody. Good afternoon to you. Thank you to the family. Thank you to Sally first and John, Sally and Jerry, John and Carolyn for making this happen. Thank you to you all for being here on this magnificent day. And thank you for making the time to listen to the story and hear what it is that we'd like to share with you today. But this is all against the background of Sally, and the story that we're going to share with you starts with Sally and revolves around Sally. This is what it is that's affecting her and the family, what's touched the lives of you all. And it's always remarkable to me, and I'm never not struck by and honored by the fact that families step up to the plate to take care of their loved ones. It's a constant source of pride in humanity that we see this in our families who work with each other to manage these very difficult and challenging diseases. So I honor you and Sally and the family for going through this the way that you are, and for taking now this extra step to work with us to try and understand better how to manage, treat, and hopefully cure this disease and those that are related to it. Is there a pointer? Thank you. Well, let's start right in the middle of this with what we understand to be this disorder called multiple system atrophy, or MSA. MSA is one of a family of neurodegenerative diseases. For some reason, either a gene that one inherits from a family member, or out of the blue, the genes somehow go wrong and the signals get crossed. Brain cells at some point in the course of a previously totally healthy person start to become abnormal. They first don't function right, and then the chemistry is abnormal, and then the brain cells themselves become abnormal under the microscope, and then they die and they move away. And these neurodegenerative diseases are the scourge of current neurology and neurobiology, and are amongst the most important of the diseases that we're facing in our civilization. And we know about Alzheimer's and Parkinson's and Lou Gehrig's disease. And the problem that I find all the time is that the folks who have a problem with the cerebellum or the ataxia feel like they've been left out, because when they say I have a problem with ataxia, someone wants to go and hail them a cab. It doesn't seem to make any sense. What is ataxia and what is cerebellum? So let's start smack in the middle of multiple system atrophy. The primary problem of MSA, of the kind that's affecting Sally, is that the cerebellum doesn't work. In this sense, what the cerebellum is doing is the coordination of motor control. It turns out that you need your cerebellum for making things better, for doing things automatically without your conscious awareness. It's always been known to be a motor control device, and we'll focus on that at the beginning. Ataxia is the word for an imbalance of gait, instability. You take an extra step, it's not so easy going down a curb. Little trouble going downstairs, you have to hold the railing. There's widening of the stance, and people stumble and then eventually fall. So ataxia is the old Greek term for instability of balance. Along with the impairment of the gait and the balance is an impairment of the coordination of extremities. One needs the dexterity and the fine motor skill to play a violin or to write or to use utensils, but there's more to the coordination of motor control than just strength. There's the ability to reach out for an object, get where you had intended, plan a structure, movement, and be able to fulfill that movement. That becomes degraded in the cerebellar motor syndrome. People have difficulty judging distances, and so the balance and the control of the arm and the leg movements together become affected. Along with that, there is an impairment of speech, because these are voluntary motor control problems, and speech is the ability, reflected in the ability to move our tongue, our lips, our palate. All of that goes together to make articulatory clarity, the diction that our teachers in school wanted us to get right. So that is a problem that goes along with the cerebellar motor syndrome, together with trouble with swallowing, and that becomes important in terms of survival and life-threatening problems. There are changes in eye movement control, so reading can become difficult. It's not a loss of vision, but the control of gaze, moving your eyes from here to there and stopping when you want to stop instead of overshooting, that becomes troublesome. It's as though the springs were too loose. When When you reach for an item, one overshoots, and there's a bounce in the movement of the arm or the leg or the gait. So that is the essence of the cerebellar motor syndrome: the speech, the arms, the legs, eye movement control, and the ability to swallow and make oneself clear. There's no problem with language. It's not a language problem. We understand what people are saying to us. We understand what words we want to get out, but the clarity of the expression is impaired. So that is the central feature of the multiple system atrophy cerebellar type. And I'll come back to the other types in a second. The other major feature of MSA as a diagnosis is another system. So the multiple systems is precisely that. The second system is the autonomic system. We have no idea the autonomic system is doing its job. It just happens. Our heart rate beats, we breathe at a particular rate, we control our body temperatures, we maintain our blood pressure as we stand up. If the blood pressure was unchanged, lying or standing, or had no response to the environment, we would have difficulty. John is a pilot. He understands what happens when you do all kind of G-forces and things. The blood pressure has to respond to that. In multiple system atrophy, the brain systems involved in the regulation of blood pressure, particularly bladder control, the degree to which we perspire or not, is affected by the underlying problem in the brain. So the autonomic component is a major second feature of MSA. The third big component is a set of problems that touch on what we see in Parkinson's disease. This is not Parkinson's disease, but it's related to Parkinson's disease. And I'll show you in a moment the parts of the brain important for Parkinson's are affected in MSA, causing slowing and rigidity and difficulty with initiation of movement. There are a few other features that are relevant here as well. There can be stiffness and spasticity, which may come out in the examination. But other findings impair patients. And when he has a story, it's a little dramatic, of a sleep disorder where people are being beaten up by their spouses in bed at nighttime. The spouse is fast asleep, and they can be thrashing of an arm or a leg. It's called a REM sleep behavior disorder. Can come on early in the problems of MSA. And it can be associated often early with changes in bladder control and in men with erectile function troubles. So these are the set of features, plus a few others, that go into the clinical diagnosis of multiple system atrophy. Early on, I'll tell you, it can be very difficult to make the diagnosis with certainty. There's no gene test as yet. There's no blood test. There's not even a brain MRI scan early on that can make the diagnosis with certainty. And so clinical suspicion and clinical ability is critical in making the diagnosis and initiating the treatments. MSA is not a common disorder. There are perhaps between 2, 3, 4 cases per 100,000 people. The mean age of onset is in the early 50s, but can come on in the 40s or late 40s, and I've had a couple of patients with whom it came on in the 30s. This is not necessarily an old person's disease. This is the prime of life. The survival has been put at around 8 years or so, but it's different now because as we understand the disease better, as we can treat the disease with different modifying agents, we can cure the problems that are symptomatic that take people's lives. So lifespan, life quality can be improved. And I'll come back to that in a few minutes. All races affected, slightly more common in males, but everybody's involved. The Parkinsonian variety is more common in the US. In Japan and the East, it's a little more common to be in the cerebelliform, the kind that Sally has. And the survival rate is somewhat similar between the two. What I'd like to do in our time is talk about the features that are at the core of this and to address some of the questions that you will be handling, that Jerry and Sally have been asked by you. What is the cerebellum? What's ataxia? What does the cerebellum do? What does it do anything other than motor control? What's actually happening in MSA? What happens to the brain? Why is there autonomic failure? And what is it that we can do at this point in the research to try and help Sally, to help people like Sally? And what does this mean for other disorders that affect the cerebellum or other diseases causing neurological devastation in the category of the neurodegenerative diseases? You've all seen the wonderful pictures of brain, where you see the picture of the brain at the top and the lovely imaging studies that show coloration and different gyri. But what's remarkable about all these lovely images is that there's nothing down the bottom. There's no cerebellum in these images. For some reason, the cerebellum got left out of our thinking about the brain. Leaving out the cerebellum is a bad idea. There is a cerebellum, and this is it. So this is a human brain from the side, and this big structure down the bottom is the cerebellum. This is a model of the brain that I held upside down. It was an article in Harvard Magazine 15 years ago now, with a model of the cerebellum sitting underneath the brain, basically in the basement of the brain. That's where the cerebellum is located. We have much more information now than we did in years past. We know what the different parts of the cerebellum are looking like. We know what the cerebellum looks like on an MRI scan. It has a very beautiful appearance. Every time I discuss cerebellum, my wife says I can't avoid using the word beautiful, but there it is. Matches my wife, so there you go. We know the appearance of the cerebellum, and we have now the new technology to investigate the way the cerebellum is wired up that is really very striking. This is a mouse. I'm not sure what the light you can see this well, but this is a mouse brain with the new technology allowing us to see that there are fibers that are moving in the white matter and in the gray matter of the cerebellum. We can actually see with the new technology the constituent elements, not just the old MRI, but the constituent elements of the cerebellum. And here is an image of a human cerebellum where you can see the cerebellar fibers connecting to other brain regions and within the cerebellum itself. So we now can identify, and we hope to be able to use these kind of new technology approaches to make diagnoses earlier than we have before. And as the clinical trials become evident, you'll be able to monitor the progression and hopefully the lack of progression of illness with these objective measures more than we've been able to in the past. This is a striking image of the fibers within the cerebellum that I produced in conjunction with my colleague in neuroimaging that shows that the entire brain, and the cerebellum in particular, has wires and pathways linking one part of the cerebellum with another and linking the cerebellum with the rest of the brain. So there's a wiring. The brain is wired up, literally hardwired. It's not just a concept. There are wires that link one piece of the brain with another, and that has relevance for SAD because it's the white matter of the brain that takes the first hit in the cerebellum in multiple system atrophy. I've been hinting that the cerebellum does more than just motor control. And what we found over the years, and described the clinical syndrome that matches this, is that the cerebellum is critical for motor control, but it's critical for the control of other kind of functions as well. It's a making things better organ. It's an old ad, we don't make things, we make things better. That's what the cerebellum does. And it does it without our conscious awareness, doing it automatically. And it's as true for motor control as it is for thinking about language, thinking about planning, organizing, and forming strategies, about visual spatial awareness, where we are in space, and about mood and feelings about ourselves and the world around us. So the cerebellum is a critical, integral member of the brain circuits through those wiring illustrations I showed you, subserving motor control critically as in ataxia and the ataxic disorders, but in other conditions as well. For example, so you can go back one. I'll show you just one example. This is the image of the brain in autism. Turns out the cerebellum is a major player, one of a number of major players in the abnormalities that go along in people who have early infantile autism. This is a new field in developmental neurobiology. The point I'm starting to share with you is that as critical as cerebellum is for ataxia and for MSA, these diseases, MSA on the one hand, and the cerebellum that it affects on the other, are at a remarkable and intriguing intersection between different kinds of diseases that affect the cerebellum and the neurodegeneration on the one hand, and different diseases that affect other kinds of systems, ranging from mood and behavior to schizophrenia. It's a completely new day in brain science, and we're looking at it from the basement up. So the cerebellum is at the critical juncture of all these aspects, and this is what we're dealing with in SALI in many regards. Let me show you some images of cerebellum in MSA specifically. These are brain scans. I don't know how well are you able to see the images with the light shining on
Yes,
the scan?
yep.
Okay. This is the normal, healthy control on an MRI scan. Here's the cerebellum, which is quite sizable in this particular image here compared to the cerebral hemisphere. In MSA, the little black regions represent the loss of the brain volume and the increased amount of space between the fold to the brain tissue. In the section here, which is the nose in the front and the back of the head here, there's a big bulge in the brainstem called the pons. The cerebellum is nice and full. In MSA, that bulge is gone and the cerebellum is smaller. The healthy brain here has the brainstem part called the pons and cerebellum. In MSA, it shrinks both in the brainstem and the cerebellum. And another section shows the same story. This bridge here, literally a bridge called a peduncle, linking the pons, the brainstem pons with cerebellum, has shrunk away in MSA. And we have this characteristic finding called the hot cross bun sign that is identifiable in the brainstem in the later stages of MSA. It's not there early on. I'm going to show you some images now of brains of people who have passed on far into the course with multiple system atrophy. It makes the point, and Vic will touch on this as well in terms of the biopsies that he's taken from some of our patients from the skin for his stem cell studies, and the autopsy studies I'm going to show you now, that by understanding what's going on in the brain, these people who have passed on and made this most generous gift to their families and to brain science have allowed us to share with you today what it is that goes on in the cerebellum and the rest of the brain in multiple system atrophy. This is just a picture from the web showing a nice big fat brain stem called the pons and the cerebellum here. And this is an image of the brain in somebody who's passed away with MSA. The pons has lost its bulge completely. The part of the brainstem down here called the medulla is also much more shrunken, and the cerebellum is tiny in the post-mortem evaluation of the cerebellum. If you cut the cerebellum in the midline, where the front is over here and the back is over here, this is the healthy, the non-diseased cerebellum. The patient is passed on, I guess no longer healthy here, but the normal cerebellum from a neurological perspective. A nice and fully elaborated mid-sagittal midline section, and here's a nucleus deep down, and this is the white matter containing cables and a nicely elaborated cerebellum. In the MSA brain, this is much smaller, and that white matter has gone completely within the cerebellum. Compare this with this, and I'll show you some slides that take you a bit further on that. Here's the cerebellum of a control brain. You can see this is the white matter within the cerebellum fold, and in the MSA brain that has disappeared, and the abnormality in the cells I'll show you in a moment. We then compare these two sections, the control brain versus the MSA-C brain. This blue line is the same area in the two brains, and it shows you the marked change in the cables that link up the cerebellum within itself and the cerebellum with other parts of the brain. In addition to that, we see that this is the healthy cerebellum, the cortex of cerebellum, where these are beautiful Purkinje cells named over 100 years ago, and a disorganization in the cerebellar cortex. And in this image here, we should be seeing lots of these little cells called Purkinje cells, and they've all gone. And around them is this empty basket. There's a complex organization of one kind of brain cell with another kind of brain cell with wiring and enveloping baskets. And when those brain cells disappear, you're left with an empty basket. And that's a reflection of the loss of these important cells in the cerebellum. In terms of the Parkinsonism that comes along with MSA, this is the healthy brain here from the neurological perspective, and this is the part that goes in Huntington's disease, which is also a neurodegenerative disorder, very closely allied to the spinocerebellar ataxias in the kinds of genetic information that is relayed from one member of the family to the next. But the putamen here is important for Parkinsonism kind of symptoms, and in the MSA brain, instead of being nice and plump, it's all shriveled up, as you see over there. This is like a neuropathology and neuroanatomy lesson. Are you all still with me?
Yes.
Similarly, in the healthy control brain versus the MSA brain, this is a nice, plump, well-organized putamen and globus pallidus. It's disorganized in the MSA brain. The brain cells are doing what they're supposed to do here in the control brain, and they've become depleted and disorganized and scarred in the MSA brain. And then one more in the series. This is the substantia nigra, which is the part that melts away in Parkinson's disease. And here in the MSA brain, the substantia nigra has become involved as well. The big plump neurons, which are healthy and looking normal here, have gone in the MSA brain in the later stages. So as a transition to what you're going to hear from Vic, we now understand, and he will tell us the story, we now understand what is the villain here. Who's the culprit? Who's to blame? So what's the smoking gun? We've known for a long time that MSA, although it wasn't called MSA until very recently, has all these features to it. I've shown you the diseased brain. I've told you about the symptoms that come about. What I haven't told you about enough, and I'll spend a moment on this now, is that many of the symptoms are amenable to treatment. And that touches on the reason that MGH takes pride in what we do. Everything we do, and I mentioned this at the outset, it starts with Sally and the story ends with Sally. What we do is we take care of patients. What makes us strong is that firstly we talk to each other. There's a very deep historical background of communication and collaboration across disciplines at the Mass General Hospital. But the ability to make the diagnosis and come up with treatments is what we care about. So we can treat depression, we can treat bladder difficulties, we can stop the blood pressure from dropping, we can stop the fatigue by different medications. There are nuances to this management. The nuances matter, and we care, and we work with that. But the bottom line of the disease cause turns out to be this villain called synuclein, and we'll hear about that from the proteins that do mischief. And it turns out that the synuclein is in the supporting cells of the brain, the oligodendroglia that John mentioned, and that are important for the integrity of the lining of the brain, all those pathways I showed you. But they also occur in the neurons, the acute Perot, little gray cells, if you like to watch acute Perot from Agatha Christie. The little gray cells, the neurons, also get affected by synuclein. And it's not only MSA that is synuclein related, it's Parkinson's disease as Parkinson's disease, not just Parkinsonism, but the real thing. Dementia with Lewy body disease and other disorders called pure autonomic failure. And you will hear from Vic how these proteins are now also tied up with other disorders, but I'll let him talk about that. So just to end off then, in terms before I close my comments, just to make the point that at the ataxia unit and in the hospital as a whole, and in our laboratory for cerebellar and neurobiology, the primary issue is to take care of our patients and provide as a good a care, a supportive environment as we can muster. We look at the role of the cerebellum not only in motor control alone, but in other aspects of function and how it touches on psychiatric illness perhaps as well. We are caring about the cause and the cure of MSA. We're targeting both these disorders, the actual, and I'll pass it on to Vic in a second. We'll hear about the cause of the biology, what the cerebellum is doing, and how this touches on other diseases that have a link to cerebellum. And this therefore leads us, again, to recognize that what we're so grateful for having you here about tonight is that you can help us recognize that we're at the crossroads of the understanding of how the brain works in the larger sense, what goes wrong in MSA, and to think about treatments for diseases as we go forward. One of the things that makes the MGH so strong as well in the whole Harvard system is that we bring into our system people who are just awesome. And Vic is one of those. And I'm delighted to tell you that he'll be joining our faculty in July next month, coming as a fellow and moving on to the faculty to work with me in the ataxia unit, whose work in understanding the biology of synuclein, I believe, is going to be pivotal in moving us forward in this very important aspect of the research program to take us into a new day and lead to a point where it's not just the symptoms we can treat, but the actual cause we can understand, improve, and hopefully cure. And with that, I'll thank you again for your attention, for coming, for the love and the care that is so obvious in this room, for Sally and for the family, and for the support that you're showing to our research program.